If your Linux-based embedded project needs to be modular, you've got to the right place. What is up, guys? My name is Branko, and today I will be demonstrating how to swap in, swap out a module in the embedded Linux platform programmatically. What's the benefit for you? You will be able to upgrade your embedded Linux platform at any time. Just plug in your add-on board into Linux-based embedded platform, and this add-on will automatically be recognized by the host. The actual driver for this add-on will be automatically loaded, and you are ready to go. To make a comparison, it is just like when you decide you need more RAM memory or better GPU for your PC. You buy the replacement, you plug this RAM and this GPU on the motherboard, you install necessary drivers, which basically means you upgraded your PC. From now on, the same upgrade logic applies for your Linux-based embedded platform as well. And how is all of this possible? Well, with ClickID. Okay, ClickID, quick recap for you guys. Should you desire to swap out modules in embedded Linux by yourself, you need a reliable way to recognize and identify them in order for proper software driver to be automatically loaded. Once again, driver will be automatically loaded, which is the crux of hot swapping modules, add-ons, devices in Linux-based embedded platform. ClickID provides this practicality, allowing you to identify and recognize modules, or dare I say devices in embedded platforms. Specifically, ClickID enables you to identify add-on boards or clickboards in a Linux-based embedded platform. Here are the steps to identify ClickID-enabled clipboards. Confirm that the embedded platform has all the prerequisites necessary for ClickID to work. Create a brief description/manifest of a clipboard. Write the manifest in the clipboard's non-volatile memory to preserve its information. Now let's be more descriptive about all of these steps. Step number 1. Check prerequisites. A Linux-based embedded board is required. Clickboard with ClickID utility is essential as well. Okay, this is how you inspect the hardware to make sure ClickID feature is available. You need to find ClickID logo and ClickID memory chip, which is going to hold the information about the clickboard. This inspection was for hardware developers. Once you found out those two, now let's make sure that software developers will be able to recognize the ClickID memory chip from within the Linux-based operating system. So, run the VS Code instance on the Linux-based embedded platform. If you want to interact with ClickID memory chip, one-wire protocol is being used. Here is a guide on how to do this. I would list all the one-wire devices connected to the platform, of course with the ls or list command. The name of the ClickID memory chip would typically start with something like this: wire 1, bus master, and the rest of the string. This means ClickID memory chip which holds the info about the clickboard had been successfully recognized by the Linux-based embedded platform. Now let's see what the Linux-based embedded platform has to say about the ClickID memory chip. If you wonder why microbus string is in this command, I'll explain it in a moment. For now, this Beagle Play, the Linux-based embedded platform, recognized this clickboard by reading the manifest file from the ClickID memory chip, which is located on the clickboard itself. Now be aware, there is a possibility that you acquired clickboard which doesn't have ClickID feature embedded on the clickboard. Let's check out this scenario. Once again, I would list all the one-bar devices connected to the platform. And this is the output which you will get if the clickboard doesn't have ClickID memory chip on it. This output indicates there aren't any one-wire peripherals on the back of the Linux-based embedded platform. Now let's perform double check once again. Let's see what the Linux-based embedded platform has to say about the ClickID memory chip. This Beagle Play tried to find a one-wire device on the microbus slot, but did not recognize any, which is as expected. Now I will reinsert clickboard with ClickID memory chip to proceed with the prerequisite for ClickID feature. Okay, prerequisite number 2. Linux-based operating system needs microbus kernel driver to be installed. Developers need to have Linux image with Linux kernel which has microbus driver installed. For the purpose of identifying clickboards in the embedded Linux environment, microbus kernel driver has been developed in collaboration with the BeagleBoard Foundation. So, to take full advantage of the ClickID, it is necessary to have a Linux image kernel with the microbus driver enabled. This is how you check whether you already have microbus driver installed in the embedded Linux environment. What you will eventually get is something like this: microbus 0 and or microbus 1, 2 or 3. It depends on how many microbus sockets your embedded Linux platform supports. And this is how you check the name of the actual driver being installed on your Linux-based embedded platform. Now, by the time you watch this video, there is a possibility that Linus Torvalds already merged microbus driver into the main Linux kernel, so you don't need to worry about installing it yourself. Linux kernel will automatically be distributed with microbus driver in it. If it is not the case, you can get the link to images with already installed microbus driver in the description down below. You will also find GitHub repository with the patched Linux which already has microbus driver merged, if you want to build the kernel image yourself. Building the kernel image is a topic of its own, so let me know in the comment section down below if you're interested in this discussion. There are a lot of online tutorials as well as ChatGPT helping you in terms of the building the Linux kernel for embedded industry, so be sure to check it out. Okay, that's about it when it comes to the prerequisites necessary for ClickID to work. Now, let's analyze the description of the clipboard, or let's review the manifest file of the clipboard. Manifest sounds way cooler than description, so I will stick to the manifest then. The topic that we are discussing now is manifest. ClickID memory chip will deliver the manifest file to the Linux operating system. Then, what happens next is proper driver is being loaded for the module which is on the clipboard. Of course, this driver has to be installed in the first place. Why? Well, this module, let's say GPS module, which resides on the clipboard, needs to receive information about the global positioning, right? Well, this module needs a software driver in order for a person to know the relative position on the planet Earth. So, this is why driver needs to be loaded, and the information about driver is stored in manifest file. And this manifest file is being stored in the ClickID memory chip, which is on the clipboard itself. And how does one manifest look like? Here is how you can find out the content of the already made manifest file, which describes, for example, GNSS7 clipboard. Let me explain the content of the manifest file itself, at least for this particular clipboard. For example, this is the name of the clipboard. This is where you type in the name of the Linux-based driver which is going to run this clipboard. Now let's talk about microbus descriptor. You will enumerate MOSI, MISO, serial, clock and chip select pins with number 5 because we are talking about the SPI pins. So we want to make sure the pin state for all of those pins to be as per SPI standards. For Linux embedded developers, make sure to check out ClickID GitHub repository to learn more about manifest files. Now let's upload this manifest file in the ClickID memory chip. First of all, clone this ClickID repository from the GitHub page onto the Linux embedded platform, in our case Beagle Play. This way, you will have access to hundreds already developed manifests at your disposal, as well as instructions on how to work with ClickID. Next, make binaries out of those manifests. Clipboard expects manifest blob or binary large object files to be uploaded into ClickID memory chip. Then, make sure you have all the binary files derived from manifest files. Then, load the appropriate manifest blob file into ClickID memory chip using the microbus driver. For example, with the GNSS7 click, you can write that manifest to microbus 0 new device entry. Now that ClickID feature is properly configured, running clipboards makes such a smooth experience in embedded Linux world. We demonstrated the capabilities of ClickID in making your Linux-based embedded projects more modular and upgradable. This ease of use, just like upgrading your PC's RAM or GPU, transforms how you interact with your embedded Linux platform. Thank you for watching, and be sure to check out the resources in the description down below for further guidance on ClickID.